Hi, this is Synthchaser from Synthchaser.com, and welcome to my 100th video. Thanks to everyone who's watched me along the way, and hopefully you'll join me for the next 100 videos. So today we're going to be continuing our restoration of this ARP Quadra. In the last video we tested out the membrane panel and determined that the membrane panel on this ARP Quadra was good. So now we're going to get underway restoring it. But before we start pulling boards out and getting busy, I'm going to give you a little background on the Quadra in case you're not familiar with this instrument, and then I'll give you a little tour of the inside. So it's called the Quadra because it has 4 distinct sections that you can use individually or in combination. It's got polyphonic strings and polyphonic synthesizer, both of which are lifted from the ARP Omni 2. In fact, we're going to see some boards inside that looked almost identical to what you'd see inside an Omni 2. So you can use the poly strings and poly synth sections in the upper 4 octaves of the keyboard, unless you've got the bass synth turned on, in which case it's just the upper 3 octaves. It's got a bass synthesizer, which makes 2 registers each of monophonic synthesizer and monophonic string bass. While the sound is similar to the Omni 2, the mechanics are a little bit different because the Quadra bass synth uses a true voltage controlled oscillator instead of the divide down stuff that the Omni does. And this is good because it means you can feed it CV inputs. The bass synth works over the lower 2 octaves of the keyboard. And finally, it has a monophonic lead synth with 2 voltage controlled oscillators, a voltage controlled filter, and a voltage controlled amplifier. And there's 1 envelope generator, which is an ADSR. The lead synth can work over the entire 5 octaves of the keyboard, or just the upper 3 if you've got the bass synth turned on. And then there's a few cool bonuses, like the preset memory, which can remember which switches you've turned on, although it doesn't remember the value of the sliders. There's what they call a sequencer, which is more of an arpeggiator. It's got aftertouch along a portion of the keyboard, and you can use that as a pitch bend or a filter modifier. But of all the bells and whistles on the Quadra, my favorite is the 14-stage analog phase shifter, which sounds freaking amazing. As with all ARPs, the Quadra's sprinkled with these dodgy tantalum capacitors, these blue blobs here, and they tend to, over time to fail by shorting out, often taking out other stuff with them. So all the tantalum capacitors in the Quadra need to go, just like we do with any other ARP. But with the Quadra, ARP started using electrolytic capacitors in places that they used to use tantalums, like these gating capacitors here for the polyphonic notes. But still, electrolytic capacitors have a limited lifespan, so we're going to replace all the tantalum and electrolytic capacitors with the capacitor kit that I've put together, which is available on my website, synthchaser.com. For this kit, I've looked at what function each capacitor serves, and I've selected a replacement capacitor with the most favorable characteristics for the job, even when it's not the same type that was originally used. Additionally, we're going to be refurbishing all the sliders and the key bed, and only after we do all that stuff, we're going to fire up the synth and identify and repair any remaining issues. So there's a bunch of boards in here, and I'm going to quickly point them out to you so you have some reference where they go after we pull them out. So we're going to start our little tour down here with the power supply. Next to it we have the upper and the lower voicing boards with the phaser sitting on top of it, and these 3 boards are very similar to what's inside the ARP Omni 2. Below that we have the keyboard electronics board. In the back we have a couple of boards that have the jacks. They call this one the tiny D-jack board, and this is the 1/4-inch jack board. Here we have that phase shifter board, which is that 14-stage voltage controlled phase shifter that I mentioned earlier. Up on the top we have the 2 boards with all the sliders. On the left is the board called the polysynth board, and the one on the right is called the lead/mix board. This little board here, well, not that little, but this skinny board here is called the microcomputer board. And then there's this interconnect board that connects the microcomputer board to the polysynth and the lead mix boards. Buried underneath, you can see it sticking out here, is a circuit board that has those red and green LEDs that poke through the membrane panel. And then finally there's a couple of little boards up here on the right and on the left that go to the left and right of the key bed that have controls for the portamento, the touch sensor, and the arpeggiator. So we're going to start here with the power supply, and they've made this power supply just about as difficult as possible for you to remove. It's got all the bolts securing it to the case under the transformers and on these heat sinks. There's the quick connect jacks that you can remove for the power outlet and switch. But then they use these really unconventional terminals there, and I'll grab the camera and take you in closer. They use these really unconventional terminals that are kind of a pain to get off, and then all the wiring is just this big rat's nest here. So even if you're able to get it off, it's a real pain to put back together. But we'll pull the power supply out, and I'll show you what we're going to do to it. So here's the huge power supply from the ARP Quadra, and it's physically very large and it's very heavy, but it's actually extremely wimpy. So you can see a resemblance to the design of the ARP Omni power supply and most other ARPs if you kind of just slice this off. In fact, this board basically contains an ARP Omni power supply over here. They have a little more room, so they spread things out. But you've got a center tap transformer, you've got a 723 regulator with a pass transistor, which on the Omni 2 does the 15 volt rail, although for the Quadra they've turned the voltages down to 12 volts. And then you have an op amp, a 301, and another pass transistor that does the negative 12 volt rail. So basically on here we have the ARP Omni power supply. But we also have a microcomputer in the ARP Quadra, so we need a 5 volt rail. And so what they decided to do is just slap another transformer, and then they actually put two of these fixed 7805 voltage regulators on there. And there's two of them because one is for the analog 5 volt rail and one is for the digital 5 volt rail. So they have separate grounds, so if they routed things well, then noise from switching, IC switching on the digital circuit shouldn't affect anything on the 5 volt analog circuit. But if you notice, this is very large, but these transistors themselves are very small, and the heat sinks are very wimpy and not very thermally efficient. I believe these voltage regulators are rated for 1.5 amps maximum, but with this heat sink that's never going to happen. And these pass transistors are also rated for 2 amps maximum, but again with this heat sink it's not going to happen. In fact, if you take a look, the rectifier diodes right here they're not even that 1N4000 series, they're 1N4148 diodes, which are rated for about 300 milliamps. So very wimpy. On the other side, for the 5 volt rail, they put 2 wimpy ones and 2 beefy ones. Overall, it's a really, really lame power supply, but for the purposes of the ARP Quadra, it gets the job done. So what we're going to be doing on this is we're going to be replacing all the electrolytic capacitors. We're going to be replacing the tantalum capacitors with new electrolytic capacitors that won't fail in shorts. And then we're going to test this out, and we're going to test it out outside the synthesizer, and I'll show you that after we change the capacitors. Interestingly, right now I have 3 Quadras here, and this one doesn't have the problem, but the other 2, both of them, the main filter capacitor here for the 5 volt rail actually leaked electrolyte. So maybe I can snap a picture and throw it up now for you to see. So I'm going to go ahead and make this power supply healthy, and then we'll test it out together. Here's a cool size comparison for these capacitors. The one on the left is the 10,000 microfarad filter capacitor for the 5 volt rail that I just took out, and the one on the right is the same 10,000 microfarads, same voltage rating, higher temperature rating capacitor that we're going to put in its place. And look how much smaller it is than the original one we took out. This is the bottom of the power supply board, and you can see that there's no ground plane, and all the copper traces are fairly thin, and we're going to use this to our advantage in mounting these new capacitors. So here's the recapped power supply, and you might be looking at it and going, what? This looks nothing like it did just a second ago. And that's because my kit includes radial capacitors to replace all the capacitors on the power supply. You'll recall a number of the filter capacitors were axial capacitors, so they had leads coming out each end of them. but I replaced them with radial capacitors, which have both of the leads coming out the same end. And you might think that I include these in my kit because I'm a cheap bastard and they cost less than the axial capacitors, but you're wrong. The reason that I include radial capacitors is because, number one, they're a lot easier to source. Very few axial capacitors are made in values this large. And then second, they have a whole heck of a lot more favorable characteristics than their axial counterparts. So these are high temperature and they have very high ripple current rating, which is something that's very important for a power supply filter capacitor. They also have a rubber cushion on the bottom, so they withstand any vibrations from charging and discharging. So what I did to get these in here is I took advantage of the fact that there is no ground plane, and I strategically drilled some holes with a very small drill bit and a Dremel in places where I could have the leads connect to the appropriate traces. So that's what's going on here. Here's the power supply from another one of my Quadras, and I also used radial capacitors, but I mounted them in a different way. Here I put them on their side and zip tied them down, soldered one lead into the correct hole, and then soldered a wire with some heat shrink over it so no one accidentally touches that, and then route it to the appropriate hole in the PCB. And whichever way you want to do it is it's your preference if you're doing this yourself. But I do feel strongly that that the improvement in the characteristics of these capacitors are worth making a kludge like this. Normally I don't like to do kludges, but this one is definitely worth it. Just for fun, I'm testing out some of these capacitors from the power supply because there are people that say recapping a synthesizer is bad advice. Well, let's take a look at this. This is the filter capacitor for the 12 or minus 12 volt rail. It's a 1000 microfarad 50 volt capacitor, and we're measuring an ESR of 0.198 ohms. And if we consult the little table here, 1000 microfarad should be somewhere between 0.07 and 0.05 ohms. So we're about 3 to 4 times our maximum allowable ESR for this capacitor. This capacitor is definitely past its prime, and it's a darn good thing we're replacing it. If you measure the same capacitor with just a capacitor meter, you'll get a good reading. So it shows that it's just a little over 1000 microfarads, and on the surface it looks good, but ESR indicates that the capacitor is bad. So I've got the power supply plugged into an AC power line here on my bench, because I like to live dangerously that way, and we're going to test this out, because it's a pain in the butt to take it in and out of the synthesizer. We want to find out if it's working, and if not, make any repairs while it's here on the bench. So we're going to test the different rails. There's 2 5 volt rails, and there's a 12 and a minus 12 volt rail. So we put the black lead on the ground, and the red lead on the rail that we're testing. And there are 2 5 volt rails. One is labeled A and one is labeled B. So we're going to put our black lead on ground D, ground B, and then we're going to put the red lead on 5 volt V. We get 5.006 volts, which is good. Now we're going to put the black lead on D ground A and the red lead on 5 volt A, and it's 5.039 volts, which is good. Now we're going to stick our black lead here on the analog ground, and we're going to test the minus 12 volt rail, the 12 volt rail first, 12.02, and then the minus 12 volt rail, minus 12.01. So they're all present and accounted for, so the test is successful. We'll do the calibration to the 12 volt rails once we put the keyboard back together and have it connected, the power supply connected to a load. But right now, for a quick check, this power supply looks to be healthy, and we can move on to the next board in the synthesizer. So next up is basically our ARP Omni 2 boards. This is the upper voicing board, the lower voicing board, and the phaser board. And they're very similar, if not the same, than what you'd find in an ARP Omni 2. The upper voicing board is the same, with the exception of this tuning coil for the master oscillator section here is mounted horizontally, so you can adjust the tuning through a hole in the back of the case instead of through the top of the case, like on an Omni 2. But otherwise, this board is the same. It's got your master oscillator, top octave generator, octave dividers, wave shapers, and then your gating circuitry here with capacitors for the top 29 notes of polysynth and polystrings. The lower voicing board is shrunken down a tad, so it has the gating capacitors for the lower 20 notes and these transistor arrays here, here, just like they are here, for gating the notes. But what we're missing is the lower 20 monophonic bass note gating capacitors, because again, that's done through a true voltage controlled oscillator rather than some cheesy capacitor and CMOS chip type arrangement that's found in an Omni 2. So this board is significantly shorter, so there's less capacitors for us to change here. And then the phaser board is exactly the same as in an ARP Omni 2. So what we're going to be doing on these boards is we're going to be replacing all the electrolytic and the tantalum capacitors with new ones. So there's some tantalum capacitors here, there's electrolytic capacitors here, another tantalum capacitor here. We're going to be changing all of those, and I'm going to be doing a visual inspection of the board to make sure there's no burned up parts or cracked solder joints on headers. And then I'm going to see if we can hook this board up to at least test to see if this part of the board is working. We can't really test the gating outside of without the rest of the synthesizer, but we can test the master oscillator, the top octave generator, and then all the wave shapers to make sure that we're getting our desired notes. And here are those three boards with their rows of lovely new capacitors soldered in. And recapping the boards also gives us the opportunity to do a visual inspection of the board, top and bottom, and inspect it for anything that looks weird. And I didn't see anything burned up or anything totally strange on these boards. But what I did notice over here on this lower voicing board, there's a really weird looking capacitor here. I had to do a double take on this, and there are 5 capacitors here in a row, and that thing there is the 5th one. Looks weird. Not what I'm used to seeing in ARPs, but we'll remember that a weird one is there in case we have problems in that area later. And on the back of another board I noticed a cut trace with a little wire here soldered to where the other one went. And it looks like that was done at the factory. You can see these chips are all the same, and coming out here of that, that's a 2, 4, 6th pin, comes over to these areas, and looks like they made a mistake on their original design. And back in 1980 or 81, it would be really costly to do a new run of these circuit boards. So that meant someone at the factory manually cutting traces and soldering jumper wires. So what I'm hoping to do here is I'm hoping to see if all these chips back in this area work. This is the master oscillator, the top octave generator, and there's some frequency divider and buffer chips here. And what I've done is I've hooked up a 12 volt power supply in reverse, so I've got minus 12 volts coming to the board. And we'll look at the output of the master oscillator coming into the top octave generator here, and that just makes a very fast square wave, which the top octave generator chip then divides down to frequencies that correspond to each of the top 13 notes on the keyboard. And I'm poking a few random ones, and it appears to be doing that. Next it gets divided down into the lower octaves of the same note and buffered. But what we're going to do is we're going to probe these diodes here. We're going to run down the little row of diodes and see that we get a kind of a sawtoothish shaped wave coming out. We do, and there's a little jitter to it, and that's because nothing afterwards on the board is connected. I'm pretty confident that when we get it plugged in, that little bit of jitter will go away. But right now we're just kind of doing a sanity check to make sure that for each of these there is some kind of output instead of a flat line, which would indicate that maybe one of the dividers or the buffer chips is bad. I'm just going to run down the row and confirm for all 49 notes we have some output. I'm not going to measure the frequency or anything like that. And it looks good. So pretty certain to say that everything back here is working okay. Obviously when we put it in and we hear the output that it makes, we'll know for sure. And that's pretty much all I can test on these boards outside the synthesizer. Testing the gating, it's just much easier just to do with the key bed in place. So we're going to put these boards aside and grab the next set of boards that we're going to work on. So next up we're going to pull the phase shifter out. You see it mounted back here in the back of the case. And we're also going to have to pull this 1/4-inch jack board out. I don't know if you're going to be able to see it, but there is one of those little blue blob tantalum capacitors on that board. So we're going to pull it out and change the capacitor. And here those boards are. This is the 14-stage phase shifter. You can see that there's quite a number of tantalum capacitors on there. This is the 1/4-inch jack board. You can see there was one little tantalum capacitor there, but we need to get rid of it. And then I also took out the tiny D jack board, the 1/8-inch jack board. I want to clean up the nuts and washers because there was some road case foam stuck on them, and just make sure that all the jacks are nice and clean this switch too. So it's always good to do a full visual inspection of all the boards. You can catch a lot of problems that way that will drive you crazy later. So we're going to be doing that with all the boards here. And now we're done with these boards. I cleaned out the jacks inside and out, and I cleaned the switch, changed the capacitor on this board, and then changed all the different capacitors on the phase shifter board. And these little audio grade electrolytic capacitors are really tiny and cute, but they need to be small because the profile of this board is pretty low. There's a little metal shield there that sits over the board in the lower part of the case. And that leaves just one more board in the lower half of the keyboard, and that's this board here, which is connected actually to the key bed, and then has these cables that go to the upper and lower voicing boards. And this is called the keyboard electronics board, and we'll remove it by taking out a bunch of screws and then pulling it straight back from the key bed. And you can see these connectors come out from the key bed. So the keyboard electronics board, like I mentioned, sits between the upper and the lower voicing board up here and the key bed down here, and basically it just passes those connections through the key contacts actually coming in contact with the bus bar, just like on an Omni 2, and the boards up here process them just like an Omni 2 with their gating transistor arrays and capacitors and whatnot. But this board also connects to the microcomputer board, and it allows the microcomputer, the CPU, to scan the key bed like a switch matrix, like in other synths like Prophet 5 and Oberheim OB series. And that scanning of the key bed is what's used to determine what note the lead synth and the bass synth should be playing. And here we're going to be changing one tantalum capacitor and two old electrolytic capacitors. And with that, we've completed the boards from the lower half of the keyboard. You can see it's quite a pile of boards and quite a number of capacitors that we've changed. Didn't really see any major signs of anything nasty having gone on there in the past. Nothing burned up, no horrible prior rework or anything like that. So things are looking pretty good. And this is probably a good place to break the video. So in the next part, we're going to continue with the upper half of the keyboard. And of course, here's the big pile of capacitors that we pulled out of the keyboard in this video today. And we're going to add to this next time. So this has been Synthchaser from Synthchaser.com. Thanks for watching, and be sure to subscribe so you don't miss out on the next part. Have a great day.